Welcome back to Chemistry 30. This is the section MS1.3, covalent bonding. So in 1.2 we looked at ionic bonding, transferring of electrons. Now we'll look at covalent bonding. Explain what is meant by covalent bonding and use valence electrons and the octet rule to write Lewis structures for molecular compounds and determine their electron distribution. So formation of covalent bonds represents another way in which elements may combine to form compounds and at the same time get that stable state that noble gases have. Rather than transferring electrons, covalent bonding occurs when electrons are shared between two or more atoms. In addition, whereas ionic bonding is simply electrical attraction of oppositely charged ions, in covalent compounds the atoms are physically attracted to each other. Compounds composed of covalent bonded groups are called molecules correctly. So Lewis electron dot structures are also used for covalent molecules when electrons are shared between two atoms. One atom donates one electron and the other atom donates a second one. So it involves donations of electrons. The shared pair of electrons represents a bond between the two. So it's like saying if you have a chocolate bar and I have a chocolate bar, we could share both chocolate bars. I could consider them to be mine and you consider them to be yours. When if two pairs of electrons are shared, we could have double bonds. So it's like sharing two chocolate bars each, or we could have a triple bond in which we each donate 3 and we have a set of 6. So if we look here, here's some examples. So hydrogen, of course. Hydrogen has one valence electron. So if they come together, they can share a set. So if I cover this up, this hydrogen considers itself to have 2 electrons. This hydrogen considers itself to have 2 electrons. And if I look at hydrogen, the closest noble gas is helium. So the most it can ever have is 2. Looking at oxygen. So if I look at oxygen, of course, oxygen, we've done that one before. It's a group 6, so it has 6 valence electrons. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. And when they come together, now, here's where we can kind of manipulate things a bit. Oxygen, each of them needs 2. They need 2. So each oxygen needs 2 electrons. So each will then share 2 electrons. So it's like I need 2, so I need to share 2 to get 2. Now here's where things get a little weird. We need to push those 2 electrons on this side so it can share with the other one. Now I know I said before that we try to make them as spread apart as possible, but when bonding comes into play, the electrons can be manipulated a little bit. So if we take a look here, each oxygen is going to share 2. So here, share 1 to get 1. There's a set. Share 1 to get 1. There we go. So we have 2 shared pairs there. So if I look at each oxygen, this oxygen thinks it has 2, 4, 6, 8. And then this oxygen thinks it's 2, 4, 6, 8. So it's stable then. Each atom considers that shared pair to be its own. And of course, we don't need to stop there. We could look at nitrogen. Now, nitrogen is a group 5 element. So if I was to draw the original Lewis structure for nitrogen, of course, it's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So they're going to come together. Now, if you have 5, you need 3 more to get 8. So in order to get 3, each nitrogen needs to share 3 electrons. So share 3 electrons to get 3 more electrons. So we're going to have to manipulate things again so that The sharing side has 3. And let's put the 2 on the other side. So yes, we're kind of bending the rules here again, aren't we? But that's okay. That's okay. So share 3 to get 3 more. So if you look at here, this nitrogen sharing this one, this nitrogen sharing this one, that becomes a shared pair. The middle one here, shared pair, bottom one, shared pair. So each nitrogen, if I look at the nitrogen on the left, 2, 4, 6, 8. It thinks it has 8. This nitrogen, 2, 4, 6, 8. So they each are considered to have a full level. Now you can see here in writing Lewis structures, the shared pair of electrons that I've circled here, so shared pair, shared pair, shared pair. Usually to make it a little easier on the eyes, it's usually illustrated as a line. So you could think of a line as being electron here, electron here, electron here, electron here. We could exchange that for a line. So if I look back at what hydrogen was, hydrogen just had 1 electron, so we could replace that with just simply that, a line in between. The oxygen that I did, see, there's a shared pair, there's a shared pair, so look at that. Shared pair, so we could exchange that for 2 lines, and then just leave the unshared pair of electrons like that. And with nitrogen, we had 3 shared pairs, so 1, 2, 3, so 1, 2, 3. Makes it a little bit easier to do. So shared pairs are illustrated by using lines, and we can have a single bond, a double bond, or a triple bond. So the sharing of electrons follows the same basic principle as in the formation of ions. Again, atoms are trying to attain the stable state like the noble gases. The octet rule states that the noble gas of electron arrangements will be achieved if the Lewis structure shows 8 electrons around each atom. With hydrogen being the exception, it needs to be like helium, which has 2 electrons. In these molecules, each atom considers the shared electrons as its own. So I mentioned that. Let's highlight that. So each atom considers that shared pair to be its own. It's just like if I have 3 chocolate bars, you have 3, and if we share them all, oh, I have 6. And then you could think of the same thing. Oh, I have 6 chocolate bars now, even though we're just simply donating 3 each. So example, H2 believes it has 2 electrons and has the same electron arrangement as helium. So we'll look at this, and those are easy examples. They're very easy, and of course these represent the Hofbrinkel elements. So those 7 elements that bond with themselves to make the diatomic gases, and we can see how that comes into play. We did the hydrogen example, we did the nitrogen example, and we did the oxygen example. Fluorine, bromine, iodine, and chlorine are very similar. They share electrons with themselves to become stable. So we've just illustrated what the Hofbrinkels do. But of course we could get more complicated, such as CO2 and molecules like that. So we have to look at a process in terms of how we can do this effectively. So Lewis structures of bigger molecules. Other molecules and polyatomic ions are also fall into that category, such as the sulfate ion, SO4 2-. How can we do that? So for larger molecules, it's necessary to determine the general arrangement of atoms called the skeleton arrangement. In most molecules, the skeleton consists of a central atom surrounded by other atoms around it. So a few general rules apply. So one thing is, if you have carbon in your example, chances are it's going to be the central atom. And that makes sense because carbon is in group 4, so it's kind of on that fringe of donating or accepting, but it tends to share 4. And to share 4 needs to gain 4, so it's going to usually bond to 4 different things if they're single bonds. So it needs to be in the middle. So in compounds with more than 1 carbon atom, the carbon atoms are joined in a chain to start the skeleton. Hydrogen, it only needs 1 more electron, right? So it's going to likely be on the outer edge. So it's never the central atom. And if I look at the halogen group, so this group here, the group 7s, they only need 1 electron as well. So they will not be the central atom either, since they only need to be bonded to 1 more thing. Oxygen, of course, oxygen is in group 6. it needs 2 covalent bonds, and it's rarely the central atom as well. And in simpler molecules, the atom that appears only once in the formula, chances are, hint, hint, wink, wink, that's going to be the central atom, the one that appears once. Okay? Now, once the molecular structure is determined, the available valence electrons must be arranged in octets around the atom. So we're going to look at valence electrons. The valence electrons of all atoms are added together. So that's one of the processes we're going to look at. Add all the valence electrons in one big pool. If the substance is a polyatomic ion, we must take into account the electrons used to form the ion. So if we're looking at negative ions, the charge represents the addition of extra electrons that must be added to it. And for cations, which are positive, we're going to look at what we must subtract from the overall structure. And a pair of electrons is placed between each 2 atoms in the skeletal structure to represent a covalent bond. These are called the bonding pairs. And then the remaining electrons are used to complete the octets of all the other atoms. Those are considered non-bonding pairs or lone pairs. All right. I think what I'll do is I'll stop the video right there since I see that we're over the 10-minute mark, and we'll come back and we'll pick up from here, and then we'll do some examples involving this.